Go ahead, Mehmet.
Thank you, Dina. Good evening. I'm Mehmet Ansoy with Denver Astronomical Society. This evening, we have Dr. Phil Kelton as our speaker. Dr. Kelton received his PhD in computer science and astronomy from the University of Texas in Austin in 1979. He had a 32-year career with McDonald Observatory, during which he was a programmer, computing system manager, assistant director, and superintendent. After retiring in 2007, he continued to be involved in public outreach, especially as a national park astronomy volunteer, primarily at Black Canyon of the Gunnison National Park. Phil is also engaged extensively in astrotourism and enjoys experiencing astronomy and telescope history firsthand, especially in France, and doing public talks when traveling. So Phil, please proceed with your presentation this evening.
Okay, well, thank you, Mehmet. It's a pleasure to speak to the group again. So let me begin by explaining that this is the third time I've done this talk. I first produced it in 2016 while I was a volunteer at Black Canyon, and I did it for the Black Canyon Astronomical Society. And I also did it again last year in September for the park, the Black Canyon National Park's Astronomy Festival, who asked me to do a talk in their festival. So that's why I have V3.0. So since this is a talk about stars, I thought I'd begin by just reminding everyone what the general structure of a typical star is. So that's the first slide. Internally, of course, you have nuclear fusion going on, fusing hydrogen into helium and higher elements depending on the star. And in the case of the sun, the energy produced works its way outward through a radiative zone, and then outer parts of the star have a convective zone, and then at the surface, you begin to have various interesting activities taking place that, of course, we observe when we do solar imaging. So the outer visible layer we call the photosphere, and then above that's the coronosphere. And we commonly observe those with our solar telescopes. We often have flares and sunspots, prominences, and various other activities, and ultimately out into the corona. So let's move on. And why is my, oh, here we go. Okay. All right. So first question, and Mehmet asked me this the other day. So why did I make this talk? And the origin of it was I started doing volunteering at Black Canyon in 2010, and I was doing it for 4 weeks every August through one full cycle of the moon. And so I'd have times when it was dark of the moon, times when the moon was very bright, times when there were no planets visible. It was monsoon season, so there'd be times when a lot of evenings it was partly cloudy and it wasn't clear whether the clouds would engulf everyone or actually go away, and we'd have a nice telescope viewing session. And so I decided in those times, I'd start talking about the bright stars. And so I finally decided to just produce a talk about some of the bright stars in the sky and learn more about them. And part of my justification was to the public, they commonly think that most stars are, pretty much alike except for their distance because they appear to be different brightnesses when in fact they exhibit a huge variety of stellar phenomena, just like the animals in a zoo. So that's the source of my whimsical title, The Stellar Zoo. So this talks about summer, in the summer evening sky, 24 naked eye stars that we will discover and learn about. Okay, so then why do I call it a stellar zoo? And that's because of this great variety of stellar phenomena. And I made a list when I produced the talk. There's a huge variety of masses and temperatures, sizes and lifetimes. Stars rotate at different rates. Some are very rapid rotators and become somewhat flattened. Large range in the densities of stars. The closest stars have proper motion, and we can observe determined distance through parallax. In the last 25 to 30 years, we've discovered many with exoplanets. Many are not single like the sun and exist in multiple stars. Many are variable, many pulsate. Many are embedded in star-forming regions and producing star clusters. They evolve, and we see them in different states of evolution. They have a great variety in their chemical structure. Many have stellar winds. The sun has a solar wind, but many have stronger stellar winds than that. Often there's mass transfer in multiple star systems. They exhibit magnetic fields and star spots and flaring, just like our sun, and then they erupt. So this is a huge variety of phenomena that we can see with stars. Okay, now I'm not going to go through this very fast, but I produced it just because we always talk about in this talk the magnitude of the stars we see, and because that's such a weird scale, I made a scale describing that. Basically, for every 5 stellar magnitudes, it's a difference of factor of 100 in the brightness of the star. So if you have a 1st magnitude star, it's 100 times brighter than a 6th magnitude star. And this is yet another one of those scales astronomers produce that's almost demonic because it's backwards and confusing. And they can even be negative like Jupiter. So at the bottom, it gives examples. The sun's minus 26, the full moon's minus 12, Venus is minus 4, Pluto's typically 13, and the Hubble Space Telescope can see down to around 30, but the night sky limit's about plus 6 to 7, typically depending on the site, the sky conditions, how good your eyes are, and so on. Okay, so what I did is I took my 24 stars and I broke them up into 4 groups. And as we go through this, in general, we're going to proceed from the brightest stars to the faintest stars that you can see with your naked eye. So let's start with Arcturus. That's the brightest star we can generally see in the summer. And I've got a constellation cartoon up here. It's the brightest star in the constellation Boötes. And often in star parties, we talk about the Big Dipper and the handle of the Big Dipper and Mizar and so on, and being able to arc to Arcturus from the handle of the Big Dipper down to Arcturus. And it's a pretty ordinary star. It is a red giant star, and so it's considerably larger than the sun, fairly close, and as kind of an intermediate mass star, it will eventually become a planetary nebula and expel its outer layers, maybe in multiple events, and the inner part will become a white dwarf, and so that's Arcturus. One of the interesting factoids is when they had the World's Fair, I guess maybe not a World's Fair, the 1933 Chicago Fair, they actually observed it with Yerkes Observatory and had a circuit that used the light from Arcturus to turn the lights on at the Chicago Fair. And it's a high proper motion star. So one of the interesting things is it has an unusual orbit around the galaxy. Okay, so let's move on. When the stars come out in the summer, one of the first things we point out usually in our constellation tours or star parties is the summer triangle. So I put an image of the summer Milky Way. On the left-hand side, you can see the summer triangle. Upper left is Altair, bottom center is Vega, or I got that backwards. Upper left is Vega, bottom center is Altair, far left is Deneb and Cygnus. Now the question at the top, it says, and I often pose this when I'm doing a star party, and I tell people once they see the summer triangle, I say, do you think they're about the same distance? And of course, because they're similar brightness, people often think, yeah, they're probably about the same distance, but they think it's probably a trick question or I wouldn't ask it, right? And so it turns out that two of those stars are very close and one is quite far. And so I'll explain it and then we'll move on. Turns out that Altair and Vega are very close, about 17 and 25 light years away, whereas Deneb is something like 1,500 to 2,500 light years away. And we'll see that in more detail. And so the conclusion from that, of course, that I tell people is that Deneb is one of the very intrinsically brightest stars in the whole galaxy. Okay, so Vega is Alpha Lyra, essentially zero magnitude. It's often near the zenith and it's very close. Turns out that it was back when they invented the standardized magnitude scale, it was chosen as the 0 point. And so other star magnitudes tie back to Vega. We'll see later how the pole star wanders around the sky with a 26,000 year period. And so it was actually once the pole star. And it has a circumstellar disk, infrared excess, and a faint companion. But to most of us, we just see it as that bright 0th magnitude star. Okay, Altair is the second star in the summer triangle, Alpha Aquili, a little bit fainter, and it's only 17 light years away. And like a lot of stars, it's variable on a very low scale, even though to the naked eye, it will, of course, appear fairly constant. One of the interesting things I found out is those of us of a certain age probably remember Walter Scott Houston's great articles for many decades in Sky and Telescope. He said it was wrapped in a galactic blizzard of planetary nebulae. And what that means is the density of planetary nebulae in this region is fairly high. And that, of course, is not surprising since it's in the Milky Way where the star density is high. It's also a rapid rotator and flattened as a result of that. And the way we determine things are rotated is from the broader spectral lines in the spectrum of the star, which are broadened by that rotation. Okay, Deneb, or Alpha Cygni, is slightly fainter yet again. And as I said before, because its distance is approximately 100 times greater than that of Vega and Altair, because of that, it's intrinsically one of the brightest stars in the Milky Way. It's the tail of the swan, or tail in Deneb is tail in Arabic. And if you figure out what its magnitude would be if it was close like Vega, it would be -8th magnitude. So it'd be incredibly bright. So again, one of the brightest stars in our galaxy with the strong stellar wind. When I was researching this, I ran across this diagram that I thought was pretty neat. So I put it in my talk. It comes from JPL and NASA. They actually did a thing called the trip around the triangle. And so in this diagram, you'll see Deneb on the left, Vega on the top, Altair on the lower right, and a key in the lower left. And they point out a lot of different objects in the summer triangle, stars with exoplanets, where the Milky Way is, open star clusters, nebulae, even a globular and even a black hole in there, SIG X1. And I always thought this might be kind of a neat theme for a star party, would be to go around and observe a lot of the different kinds of objects in the summer triangle to go deeper. Okay, finally, the last of my first set of stars is Antares, which is Alpha Scorpii. And it's a highly evolved red giant, supergiant actually, and it's quite a bit further away than Vega and Altair, over 600 light years, and it does have a fainter companion. And one of the fun things I like to tell people is the origin of the name is that it's a, quote, anti-Aries, and Aries, of course, refers to Mars, and because, oh, sorry, the dog is barking. Hopefully he'll stop or my wife will take care of him. If you pay attention to Mars, and it has a 26-month cycle when it has an opposition every 26 months, it's typically in a similar declination to Antares. and but its motion varies widely as it goes back and forth along a region left to right. And so whereas Antares is always there in Scorpius, Mars moves around on this plane back and forth relative to Aries. So that was my understanding of where the name came from. It's a very massive star, 15 to 20 solar masses, quite young. And of course, because it's very massive, it's going to have a short lifetime. And it illustrates the fact that fact illustrates the point that there's roughly a 3 order of magnitude difference in the masses of stars, from down about 8% of the mass of the sun up to roughly 100 times the mass of the sun. And because it's very massive and quite young, it's a supernova in waiting. And that's in astronomical terms, it will go supernova fairly soon. There are also other supernova progenitors in the stinger of Scorpion. This is a nice image from Chandra of a supernova, Tycho supernova, and that's kind of an illustration of what Antares may look like someday. Okay, so my second selection of stars out of my 24, I called, quote, fun stars, unquote, for various reasons: Polaris, Mizar, Thuban, Algol, Zubenelgenubi, Caroli, and Beta Cap. Okay, so Polaris is the first, which of course is the pole star. It's the current pole star, half a degree or so from the true North Pole. And because of that, you can use it to estimate your latitude. Black Canyon's about 38 degrees north. I think Denver's slightly higher. Where I live in Texas is about 30 degrees north latitude. And when I'm talking to people in the star party as it's getting dark, and of course, one of the things I say is, now, where's the North Pole? Can you find the North Pole? And once they figure out how to find that, I say, once they figure out where north is, I say, okay, now how far above the horizon do you look? Most do not realize that the distance above the horizon equals your latitude. So in Black Canyon or in Colorado in general, this can be around 38 to 40 degrees north. It's a nice double star. William Herschel first saw that. It's the brightest Cepheid variable in the sky. So it's a pulsating star with about a 4-day period. Another thing that I've noticed is, and it's also surrounded by a faint, what's called an IFN, an integrated flux nebulae. And it's pretty common, for example, in the Orion Nebula, that you'll have a small number or a single star illuminating a gaseous nebula nearby the star, and that's how we see the nebula shine. But these things called IFNs are actually illuminated by the integrated light from the galaxy in general. So if you look up images of Polaris and its IFN, you'll see this faint IFN around Polaris that becomes very impressive in a longer exposure photograph. All right, so let's move on. Mizar and Alcor, of course, are commonly observed since Mizar is such a nice double. This is just a sketch from a guy named Jeremy Perez, and we've all seen Mizar and Alcor, handle of the Big Dipper. Here's our diagram again with the Big Dipper, the middle star in the Big Dipper. So it's easy to find. And it's also a fairly nearby star, about 80 light years. And it was the first discovered double star back in the 1600s. And it's more than meets the eye because it's really a quadruple system. And Alcor, which may or may not be in the Mizar system, if it is, and Alcor may also be a double, it could be as much as a sextuple star, a star with 6 elements. I think the jury's still out, as far as I know, on just exactly how many stars are in that system. And the last note talks about the fact that some of these double stars are discovered spectroscopically, and in which the lines in the spectrum are not just a single set from a single star. If it's a double, they're actually 2 sets of stars that move around in a high resolution spectrogram by a very small amount. and that indicates the orbital motion. And there's really more stars spectroscopically there than meet the eye visually. Okay, Thuban or Alpha Draconis, we're getting fainter now, down to third magnitude, is another star. And Thuban is kind of midway between Mizar and the bowl of the Little Dipper. And the interesting thing about Thuban is it's the once and future pole star. And back about almost 5,000 years ago, it was actually the pole star back at the time of the Egyptians. And it's about 300 light years away. And this next diagram illustrates how the North Celestial Pole goes around a cycle of about 26,000 light years. So at the top center where it says plus 2,000, that's where Polaris is and the Little Dipper. Over on the right side, between minus 2,000 and minus 4,000 is where Thuban is located, and that's where the pole star was located back in the time of the Egyptians. And then the chart shows other stars in the sky and when they either were or will be the pole star. Okay, my next star is Algol or Beta Persei, the demon star. And of course, the name derives from the Arabic for demon. And because it's fairly bright, second to third magnitude, and exhibits this continual brightness variation because it's an eclipsing binary. That's why it was given the name the demon star. It's one of the most famous variables, and because it's fairly bright, it's been known to the ancients, literally for thousands of years. So it was the first discovered and the brightest of the eclipsing binaries. So it exhibits two eclipses, a primary and a secondary, and with a period of just under 3 days. So the next slide gives an illustration of this. A couple of things here. In the upper right is a diagram from over 100 years ago showing the fact that it has both this primary and secondary eclipse, depending on whether the brighter or fainter star is eclipsing the other star. At the left is an illustration of a comparison star chart, and I'm sure many of you are familiar with, but maybe not all of you, with how people who estimate or study variable stars, they do it by comparing the brightness at any given time with companion stars of essentially a fixed and known magnitude. And the lower right shows an example from the AA VSO, the American Association of Variable Star Observers, showing how eclipses occur from that kind of data. Okay, next we have good old Zubenelgenubi, Alpha Libra, also just about third magnitude. And I later call it my Hall of Fame name star. Again, in the summer sky, Libra is to the west of Scorpius, and it's fairly bright. And so in a star party, while you're waiting for the sky to get dark enough to look at the typical kinds of things you look at in a star party for the public, Zubenelgenubi is a good one to point out. And the name actually derives from the Arabic for southern and northern claw. So if you imagine Scorpius, the scorpion, extending beyond to the west, the form we typically see, the claws could be visualized as Alpha and Beta Libra, where Libra is our modern constellation. And so it's the north and south claw. It's actually a wide double star, beautiful binocular double, and the public also likes that when you tell them it's Zubenelgenubi. Okay, two more of my so-called fun stars. One is Cor Caroli, the heart of Charles, I think it's called, Alpha Canis Venatici, or Venatici. I don't know how people say that, but I call it Alpha Canvan. And it's a beautiful double star. And it's actually fairly far away from the plane of the Milky Way in a region that's really largely dominated, at least from the amateur observer's point of view, by brighter galaxies and in a much less dense stellar population. But it's a very nice double star and fairly close and not too far from the Big Dipper. And if you do a little research, the name means the heart of Charles. And what I found out is it was named in 1660 when Charles II took the throne in England. And of course, if you know any English history, poor old Charles I lasted until 1649, and then the English Civil War continued for a while. So it wasn't clear to historians whether it was named in honor of Charles I, the previous king, or in honor of Charles II when he took the throne. But anyway, it's the heart of Charles. The bottom section, it does have chemical abundances that are peculiar, strong magnetic fields and star spots. And astrophysically, it's a very interesting star. But we mostly see it as that beautiful double star. Okay, the last one in this set of stars is Beta Cap, and Capricornus. And just like Zubenelgenubi, it's a wide, bright visual double, just east of Sagittarius. Again, it's excellent in binoculars. And so in these star parties, when I'm explaining things like this, if people have binoculars, I always tell them, look at it with your binoculars. You'll be surprised at how nice a view you get of these bright visual binary doubles. It's also called Dabih Major and Dabih Minor. And one of the interesting things I found out about this star was, again, kind of like Mizar, it's a much more complex system that meets the eye. At least 5 stars. And Stardate, which some of you may hear on the radio, it's actually produced by McDonald Observatory, for whom I worked for a long time. In the Stardate's piece about Beta Cap, to quote, they said, its orbital motions make you dizzy. And I'll leave it at that. If you're interested, you can study Beta Cap some more. But a complex star that appears quite simple through binoculars. Okay, so to recap my quote fun stars, Polaris is the North Star, Mizar, and I forgot to say this, the eye test of the ancients. A lot of people do this in their star parties. When they point out Mizar, they say, now, can you see anything else interesting about Mizar? And some of them with good eyesight say, oh, there's another fainter star right next to it. And then you say, well, the word is that it's the eye test of the ancients, the Romans, the Egyptians, whoever. And if you have glasses and can see that, that's great. If you take your glasses off, it all becomes a fuzzball. You can understand why that might have been an eye test. I don't know if that's true or not, but it makes a good story. Okay, Thuban, the once and future pole star, Algol, the demon star, Zubenelgenubi, the great name, Corcoroli, and Beta Cap. Okay, my third set of stars are from Cygnus, and I picked out 4 favorites: Alberio, 52 Sig, 61 Sig, and P Cygni. And I'm going to take a drink of water. It, of course, is obvious why Alberio is on the list. And maybe some of you recognize the others. We'll see. Okay, so here's a nice visualization of Cygnus from Cosmic Pursuits. So in the upper left is Deneb. You see the Northern Cross going from the upper left to the lower right where Alberio is located. So you see not only the Northern Cross, you see the swan, Deneb's the tail, Alberio's the head as it flies down the Milky Way toward the center of the galaxy. Okay, so Alberio, of course, is the showpiece double, yellowish and bluish. The thing I always tell people about Alberio is that it's a nice illustration of star temperatures. So the bluer star is the hotter star, the yellowish star, which is the brighter of the two, is not as hot on its surface temperature as Alberio. Turns out the blue star is a rapid rotator with an equatorial disk, and the yellow star is a very close binary. So once again, what looks like a simple, pretty double star is actually a much more complex object. Okay, the next one, 52 Sig, is interesting because it's a signpost for the Veil Nebula, one of the most famous objects in the sky, and a supernova remnant. So in the upper right, I have a little illustration from a star chart, and you can see 52 Sig in there as a double star, and the several obvious parts of the Veil Nebula, the supernova remnant that covers several degrees of sky. On the left, this is one of the images I've taken in the last 2 years during the pandemic. Turns out before the pandemic in November 2019, I purchased a Nikon D750, which is a quite good astronomical camera. At the time, I was really more interested in doing landscape photography and maybe experimenting with some imaging through my telescopes. But the last 2 years, I've done a lot of imaging of single 25-second exposures through several of my telescopes and through several filters. And this is one I took with a 3-inch telescope through an optolong L-enhanced filter with a 0.8x focal reducer, 25 seconds. I live about 5 miles from downtown Austin, Texas, which is the last time I saw the population, it was 2.3 million. So it's not quite as big as Denver, but it's not that far away. So I live in a highly light polluted sky, Bortle 8 or 9, depending on exactly where you are in my neighborhood. But the fact that you can see the veil, even from my light polluted site, is a pretty amazing testament to what modern technology can do. So good old 52 Sig is that star up near the upper right, foreground star to part of the veil. Okay, my third one in Cygnus is P Cygni. On the left is an illustration from Sky and Telescope, and 61 Cygni is off, I guess that's not too far from Deneb and the Veil Nebula. And it's one of the closer stars, about 11 light years away. And its claim to fame, or one of its claim to fames, is it was the first star to have its distance measured by the technique of stellar parallax. This is an illustration that I found on the web of how stars appear to be at a different distance because of parallax, if they're close enough, as the sun, as the Earth orbits the sun. So in the two extremes of the Earth's orbit, the star will appear to have a slightly different distance because of parallax. Now you can also tell people to understand parallax by taking your arm and extending it and closing one eye and then the other and looking at a close object like a tree in your yard or something, and you'll see that object appear to be in a slightly different place. Well, that's the same principle that was used to measure the distance of 61 Sig. Well, this next slide illustrates how that happened. This was done in 1838 by Bessel, and here's a portrait of Bessel. And he amazingly determined the distance of a little over 11 light years away to within 15% of today's value, and almost 200 years ago. And its actual parallax is just a little bit less than 0.3 of an arcsecond. And so he actually made large numbers of observations over an extended period, of a whole year or more. And by doing lots of statistics, he was able to actually determine that the distance on the sky, the location on the sky varied by about 1/3 of an arcsecond from one end of the Earth's orbit versus the other, and determined that distance to within 15% of today's distance. So 61 Sig is actually one of my favorite stars, just because it's a beautiful wide double star. Both stars are yellowish, similar to our sun, almost identical in appearance, and a very nice star to look at in your small telescope. Okay, the last one's P Cygni. In this diagram of Cygnus, it's shown just below Gamma Cygni, where the little red circle is located. And P Cygni's claim to fame is it's one of the stars with the strongest stellar winds. We're getting into the fainter stars now. It's about almost magnitude 5, although it is variable. And it's actually quite far away, and it's just like Deneb, it's one of the most luminous stars in the Milky Way, roughly 6,000 light years away. And it has this strong outflow or stellar wind, similar to the sun's solar wind, but much stronger. And effectively, it's a permanent or slow nova expelling material. On the right, it's a thing called the P P Cygni profile. And these kind of stars, what they do is the gaseous nebula around them gives an emission, which is the emission part of the profile, but the part of the gaseous nebula that's coming toward us absorbs material with a blue shift, and that's the left part of the profile. So this very distinctive profile in the stellar spectrum of a P Cygni type profile is how we know it has this strong stellar wind. Okay, finally, I've got 8 more stars, which I thought were interesting for other reasons. So we'll work our way through those. First one is Beta Lyrae. Beta Lyrae is a very interesting star. This is a light curve from Jim Kaler, who was an astronomy professor at the University of Illinois for a long time. And he wrote a fascinating book called, I think, The 100 Greatest Stars. And it's quite a fascinating book if you're interested in stars. But it has an almost continuously variable in brightness. And it's in Vega, or excuse me, it's in Lyra near Vega with these continuous brightnesses. It's intensely studied, but from what I can tell, still not very well understood. It is an eclipsing binary, but apparently has other companions. And with a lot going on in this system, tidal distortions, mass transfer, accretion disks, and so on. So the very complex object, and which looks fairly simple to the naked eye. The next one's Delta Cepheus, Delta Ceph, very famous star because it's the most famous and the prototype star of the Cepheid variables. In this excerpt from an atlas, if you look in the bottom center, there's a little triangle of stars. It's the leftmost of the triangle, Delta Ceph. It's also a double star, and it's bright enough, although in my sky, which is about 4th magnitude on a good night, it's a little hard to see that triangle, but in a good sky, that triangle really stands out. So it's easy to pick out Delta Ceph visually with your naked eye. So it's the prototype star of this important class of variables, the Cepheids, discovered several, the variability discovered several centuries ago. It's also a very nice, bright double star. And it's what we call a standard candle. So back in over a century ago, Leavitt published determined what's called the period luminosity relationship and discovered that the absolute brightness of the stars related to the period. So if you can measure the period of Cepheid variables and you know their apparent luminosity, and you can know their absolute luminosity, and from that you can just determine their distance. And of course, Hubble discovered Cepheids in Messier 31, the Andromeda galaxy, back in 1924. And by determining its distance, this is how he determined that the Andromeda galaxy was a separate galaxy outside our Milky Way galaxy. And so the cosmic distance ladder determines distances in the universe by an increasingly further away set of methods. And so it's a key part of that distance ladder. My next star is pretty close by, also in Cepheus, Mu Ceph. It's also known as Herschel's Garnet star. It's a variable, 3.4 to 5.1 magnitude over a several-year period, so it's easily visible to the naked eye. And it's also one of the largest and brightest stars in the galaxy, and it's very red. And so you may or may not be able to determine the redness of it from your naked eye observation. But in a telescope, red stars like this are really pretty neat because they stand out. It's about 40 solar masses, so it'll be a supernova, and it's one of the best naked eye variables that you can observe without a telescope. I list several others: Algol, Beta Lyrae, and Delta Cepheus being 3 of the other best naked eye variable stars. This next one is an illustration not of Mu Ceph, but of another very large supergiant star, VY Canis Majoris. And in it, you can see how small the sun is relative to the huge size of some of these supergiant stars. Time for another drink. Next star, which is also visible to the naked eye, is Rho Ophiuchus. or rho Oph, as I call it. It's very near Antares, and on the left is an illustration of, in the lower left is Antares, and the upper part is where rho Ophiuchus is located. And this is a very commonly observed object by astroimagers who take beautiful images because it's an intense star forming region. There's also dark clouds around it. And to boot, it's a very nice close double star of 2 fifth magnitude stars 3 arcseconds away. So if you're into double stars, this is a pretty neat one to observe. I've also looked at this with my camera in the city, and you can get a nice image of the 5 stars in this pentagon, which stand out in the good sky, and rho Ophiuchus, which feels like it's in Scorpius, but it's really in Ophiuchus, is easy to spot. Okay, the next 2 stars are from Corona Borealis, so we're back to that cartoon again. Corona Borealis being pretty near Boötes, the northern crown. So the first one is Alcor Bor, R being a designation that it's a variable star, and it varies with a variation of almost 10 magnitudes. So at its brightest, it's about magnitude 6, and it would be visible in a good dark sky to a good observer. You can see it's kind of in the middle, a little bit to the left in Corona Borealis, the northern crown. And what it's called is a reverse nova, and it's believed there's a city mass that is around the star that sometimes makes it fade out to a very faint magnitude. So it's a disappearing star. It's almost 5,000 light years away, and it's believed to have this shell of carbon particles and a sooty nature, which cause these magnitude drops. Here's a light curve from back in the 1940s, where you can see at the top, when it's fairly constant, it's about 6 magnitudes. This light curve goes over about 10 years, and every so often it exhibits these really interesting drops down to 12th or as low as 15th magnitude. So that's a very unusual and interesting star. The next one, I called it a bonus star because generally speaking, you cannot see it with the naked eye, but occasionally it does the opposite. It's a recurrent nova, and it's usually about magnitude 10, so it's way too faint for the naked eye, though, of course, you could easily find it in a small telescope. But every now and then it brightens substantially to the examples given here, 2nd magnitude in 1866 or 3rd magnitude in 1946. With lesser eruptions in 1963 and 75. So it's a red giant orbiting a white dwarf, and the giant feeds the white dwarf, and as material accretes, they eventually cause these explosions, and if enough matter accretes, it could even potentially go supernova. Okay, I think I've got 2 stars left. The first one's 51 Peg, and 51 Peg is about 5.5 magnitude. In this diagram, you can see the great square of Pegasus, we call it, on the left, and it's about midway between Alpha and Beta Pegasus. And because it's 5.5 magnitude in a good dark sky, you can see it with the naked eye. Well, its claim to fame is it was the first star for which an exoplanet was discovered. And this poster on the right was NASA's poster about 51 Peg B being the first exoplanet. So this next slide kind of summarizes what happened. It was discovered in 1995, so that's 27 years ago. And there were Swiss astronomers using the radial velocity method so they could actually determine that there was another object orbiting the main star, and they could determine that it was an exoplanet. It was actually discovered in France and Provence with a telescope of about 2-meter aperture, fairly close by, 59 light years away, with a couple of unusual names there. And in more recent times, the spacecraft Kepler has resulted in the discovery of thousands of exoplanets, and many of those were deemed to be potential exoplanet stars, and which were then later confirmed through through ground-based follow-up. And last time I looked, there were over 4,000. That was a few years ago. So that number grows constantly, the number of confirmed exoplanets. Okay, my final star, and this is kind of a joke, but it's my artist concept of my last star, which of course is a red dwarf, a small red dot. And so this star is was discovered by Lacaille in the southern sky. It's at minus 39 degrees declination, and it's about 6.7 magnitude. So again, it's at the limit of observability by a good, really sharp-eyed observer and a good sight on a good night. And so it's theoretically visible to the naked eye. But the reason I included this is that red dwarfs, of course, are the most common stars in the Milky Way. They're very low, fairly low mass stars. This one's only about 0.6 of a solar mass, but and quite close. But this large number of very common red dwarf stars are mostly not seen by us to the naked eye because they're so intrinsically faint. And because they have low masses, they have very long lifetimes and billions, possibly even trillions of years, who knows. And because those temperatures are so low relative to most stars, they're burning their nuclear fuel fairly slowly. It's in the constellation Microscopium, south of Copernicus, so theoretically visible, easily visible and findable with binoculars if you have a good view of minus 39 degrees declination. Okay, so this is my last slide. My conclusion is go out and have fun with the bright stars, what I call the stellar zoo. My last slide is the Milky Way. I took this at McDonald Observatory last summer in July. It's a picture of the Milky Way over the 107-inch dome at McDonald Observatory, where I spent a lot of time working in my career. So that's my last slide. And thank you for listening. And I'm happy to entertain questions.
Thank you very much, Phil. This was a very, very comprehensive and informative presentation here. So you covered the summer skies quite well. One question that I wonder about is whether you have a similar presentation for the winter skies.
The answer to that is no, and I'm trying to get my cursor to appear. Let's see, I can do escape, actually. There we go. Now I can stop sharing. Okay. The answer is I've thought about producing that, and I may yet produce that. Haven't done it yet, but I think that would be really fun. Obviously you've got Sirius and the Pup, and you've got Betelgeuse, and you could go on and on. All kinds of interesting stars in the winter sky, and I may yet do that because it was a lot of fun to produce this talk and do the research that led me to this this slideshow.
Actually, some people claim that the winter skies are even more interesting than the summer skies. I don't know whether that
I would say they're equally interesting if you're willing to delve into a lot of details. Yeah, the winter sky is great.
Okay. Are there any questions? Let me check. Yeah, Sam says, nice presentation, a lot of info I forgot I knew. Well, if you forgot,
Yeah.
I guess we all have the same problem.
Steve Warren has his hand up.
Yes, Steve. Unmute, please, Steve.
Okay, sorry, just took me a second. I have a couple, well, the questions that I had first was about Corona Borealis. With that much of a magnitude change, but however your descriptions indicates that it's not a Mira variable. And a little bit more, I guess I was a little bit unclear. You say, was that the result of carbon clouds in front of it, or is it actually a carbon star?
I think that's the result of carbon clouds in front of it. I think the bottom line is that it's soot and carbon is maybe a theory, and I'm not sure how well established that is, but that was my my conclusion from doing a little research on the star. Remember, I generated this talk 6 years ago, so I haven't really looked into the details behind Arcor bore in a while, but that'd be an interesting topic to look into.
Yeah, they're changing all the time. And if you don't mind, I have another question on the first chart about the sun.
Okay.
Okay, what we see, of course, in the photosphere and the surface of the sun, the temperature around 5,800 Kelvin.
Mm-hmm.
Although the corona, we end up with temperatures in the millions of degrees.
Mm-hmm.
And they believe right now that is because of acoustics. In other words, sort of like mounting a whole bunch of 1,000-watt speakers on the sun. And my question is, has that been proven, or has there ever been any experiments to confirm that acoustics actually can produce heat?
Okay. My answer to that is I think the Parker Solar Probe is probably going to answer that question. You remember a couple of years ago, the Parker Solar Probe was launched, and it's the first of the spacecraft that was designed to go in close to the sun and actually orbit around in the region of the corona. And I believe one of its main science missions was to understand some of the reasons why we have that high temperatures. And if that's I'm not particularly familiar with this acoustic theory, but I think over time the Parker Solar Probe will probably answer that question. So
Okay.
I don't know if it's produced any preliminary results yet or not, but I think that's where I would start looking.
Okay, well, thank you very much. That will give me somewhere to look.
Okay.
There are a couple of comments here. Jack says, great presentation, very comprehensive, which I totally agree. Excellent. And Adam says, fantastic presentation. Thank you. So you have at least several people categorizing you as a fantastic presentation and presentation giver.
All right. Well, thank you for the compliments.
Any other questions from the audience? I think I'm not seeing any. And Steve Barr also says, great job. And I guess we all have to do, what we need to do is take our telescopes out and go and observe those things in the summer, as long as the weather permits.
And of course, binoculars are a great way to observe a lot of these guys. Some are, as I pointed out, are doubles, and Ceph is a reddish star, and Algol, you can, if you find the ephemeris that shows you when the minima will occur, you can actually observe the eclipses with your naked eye, but they'd be even better with binoculars. So I would certainly recommend binoculars for a lot of these.
Right. Well, if there are no other questions, we would like to thank you, Phil, for the excellent presentation, and we will definitely study the charts as well, provided that you can send me a copy. We managed to send me a copy and put it in our library, as I mentioned to you before.
Okay, I'll plan to do that.
Okay, thank you very much, everyone. And we can end the live streaming and recording.